Okay. Good morning, students.
Good morning, sir.
Yeah, so it's 9:05, so I'm starting the class. I'm seeing that there are 14 students present right now. Okay. So now, if you recapitulate what you have done in our last class, we were discussing axisymmetric system, and then we developed the equation for axisymmetric system with equal nodal distances. But at the same time, with the help of examples, I tried to explain it to you that if we use equal nodal distances, then the total number of nodes, etc., becomes too large, and uh, I mean it's a problem. So what we have to do, we have to find a practical compromise, and we do it through unequal nodal distances. And when we say nodal distances, last class there was a question that whether it is diagonal distance. The answer is no. It is the distance between two nodes which are connected. So it is either horizontally or vertically. That means either in x direction or in y direction. And if it is three-dimensional, either in x, y, or z direction, not in the diagonal direction. So I start today's class with the development of the equation with unequal nodal distance in the axisymmetric system. Now, this one, as a matter of fact, the derivation is very much similar to what we have done. Only thing is, once again, if you recall that for unequal nodal distances, we find out which one is the largest nodal distance. And then we call that to be as h, and all other nodal distances are represented as a fraction of that nodal distance. So hopefully you can see the file on your screen where it is shown that our target node where we are going to write the FDM equation, node 0, is connected to four other nodes. By the way, axisymmetric system is always represented on a two-dimensional plane. It is never represented as three-dimensional because here the symmetry is rotation. Rotation about the axis of symmetry. That is shown on the left-hand side. This is S is the axis of symmetry. So we represent the nodal distances which are all less than h as a fraction of h, and then S1, S2, S3 and S4 are nothing but dimensionless quantities which is less than 1. So following what we have done earlier, we write the Taylor series between node 1 and node 0, and then node 3 and node 0. Now our target is to find out the term del 2 V del R square and del V del R. So that is algebra, so you can do that. I am not going into the algebra part, although in the note it is given very clearly. And if you do that, you arrive at equation 37. That's for the second order derivative, that is del 2v del r square. But then we have to find out also del v del r from equation 35 and 36. So we eliminate del 2v del r square, and we arrive at equation 38, which is del v del r. But the term which is in the Laplace's equation represented in cylindrical coordinates is not just del v del r, it is 1 by r del v del r. Now, what is R? R is the distance of the target node from the axis of symmetry. That means in this diagram, this is the target node. So, what is the radial distance from the axis of symmetry? Naturally, this will be more than h. So, this is represented as a dimensionless number s multiplied by h. Now, this s is not less than 1, it could be anything. So, here you can see in equation 39, 1 by r del v del r is represented as 1 by sh del v del r, where s is a dimensionless quantity, similar to s1, s3, etc. So in this way, we get the expression of 1 by r del v del r. Then you apply Taylor series between node 2 and 0 and 4 and 0, which is in the z direction. This is earlier it is all in the r direction. And we write down what is del 2 del z square. That's the third term of the Laplace's equation in cylindrical coordinates. So these three terms as the first equation, although it looks pretty big, but if you look carefully, these are the three terms uh, as developed earlier. Here you can see here equation 40. That's the last term here on your screen. Then you can see here that 39. It has two terms. These are the second and the third term. That is 1 by r del v del r. Then the first term here is del 2 v del r square. So then we do a lot of algebra, and finally we get an expression, equation 41. Here, if we again look at it, we see that the equation involves only electric potential and dimensionless numbers. So therefore, it is a linear equation as well as it involves only scalar quantity, which is always the target of this method. Now, I just want to tell you one thing that if you do this derivation yourself, this algebra is such that you might arrive at a slightly different way of representation. That does not mean that you are wrong. It is the way I have derived it. But you can also do that and find out what is V0 in terms of V1, V2, etc. and S1, S2, S3. As I have told you that when the target node 0 is on the axis of symmetry, then r is equal to 0, and then the second term of the Laplace's equation, which is 1 by r del v del r, that becomes undefined. Now that is not possible to solve, so what we do, we modify the Laplace's equation. And once again, for recapitulation, since the axis of symmetry is the axis of asymmetry represents the rotational symmetry, so of 360 degree, so any flux line that will be only on the right hand side on this diagram, because if it crosses the axis of symmetry, then the the rotational symmetry will be lost. So on the axis of symmetry, the flux line is tangential to the z-axis. And flux line is nothing but the resultant of the first order derivative of electric potential, which means the electric field intensity component. So if you take del V del R, it's the R component. On this diagram, it will become horizontal. If you take del V del Z, it will be the Z component, and that will become the vertical. So then, along the axis of symmetry, since the flux line is tangential, so we say that del V del R is 0 because otherwise it cannot be tangential. Or in mathematical terms, we say that if r tends to 0, del v del r tends to 0. And therefore, applying L'Hospital's rule, we can say that limit r tends to 0, 1 by r del v del r becomes del 2 v del r square. So we get a modified Laplace's equation for the node on the axis of symmetry, which is 2 del 2 v del r square, because the second term is also del 2 v del r square. Now here I have to say again that for a two-dimensional system, when we take only half of this plane, then we say that there is a symmetry on the left half. But for axisymmetric system, there is no half symmetry. It's a rotational symmetry. So our configuration is always on the half of this plane. And the z-axis is always the axis of symmetry. So for a node 0, which is on the axis of symmetry, only 3 connected nodes will be there, 1, 2, and 4. The node 3 will not be there. So we apply Taylor series between node 0 and 1, and we get this expression. And del v del r is 0 because here r is 0, so second term is 0. So we get this expression. Here we have written that at r tends to 0, del v del r is 0. So we get equation 42, where 2 del 2 v del r square is one term of the Laplace's equation. Similarly, you write down the Taylor series for node 2, 0, and 4 and get an expression for the del 2 v del z square. And then you put everything together and then simplify the whole thing. You get equation 43, which is the FDM equation for axisymmetric system with unequal nodal distance, and when the node 0 is lying on the axis of symmetry. Now here is a problem that I have given, that previously in the two-dimensional system I had given the same problem, but here it is an axisymmetric problem. So therefore, this half circle, whatever you are seeing, now this half circle is this half circle, what is the actual geometry? Actually, I should not have drawn this left hand side. That's a mistake on my part. I should have done on the right half of the plane, because it is rotationally symmetric. So this quarter circle, if I rotate it around the axis, I get the volume. And what you get? You get half sphere. If you recall, I said in the two-dimensional system, the field is independent of z-axis if this is translated along the z-axis, where the z-axis is perpendicular to the plane of this computer or whatever you can say. And when this circle is translated, we get a cylinder as the volume. But here it is rotationally symmetric. So when we rotate this circle around the axis of symmetry, we get a sphere or a half sphere, whatever it is. So this is the problem, exactly same as that previous one. Only difference is that this is a rotationally symmetric system. And if you look at the nodal distances, we find that 1, 2, then there is a mistake that node number 5 is missing. 4 and 5, they have all equal nodal distances, and node number 3 here has unequal nodal distances. So when we write the equation V1 and V2, that means V1 and V2, I can use the equation for equal nodal distance, which we discussed in our last class, and that is this equation. And node 1 and 2, you have to remember, is lying on the axis of symmetry. So we have to use the appropriate equation. Similarly, Node 4 and 5, here you can see node 4 and 5, that is here node 4 and 5, they have also equal nodal distances, and so we can use the equation developed in our last class, that for the node when it is lying away from the axis. Because remember, in axisymmetric system we will always have two equations, one for the node lying on the axis and one away from the axis. Finally, the node 3, here we can see that the nodal distances between the 1 and 0, 3 and 0, 4 and 0, they are all same. So S1, S3 and S4 will be 1, whereas S2, here it is given 0.5. So we can write the equation for V3, where we take, here you can see S1, S3, S4 is 1, S2 is 0.5, and at the same time we have to understand that 3, 4 and 5 are lying away from the axis. So there will be always a question of the radial distance from the axis of symmetry, which is represented in terms of h. Now since this is h distance from the axis of symmetry, so r is equal to sh, and therefore s is equal to 1, and that is what it is shown here. So with all this information, then it becomes very straightforward, and we can use the formula for the unequal nodal distance in axisymmetric system for a node lying away from the axis. And this is that equation here, V3. In some examples of the problems, we don't tell you what is the value of S2. For example, here I have shown a discretization. Now you can clearly see that the nodal distances are h, which is r by 2. Whereas for this node, if you can see my mouse moving, this S2 is not given, but then it is quite possible that using your knowledge of trigonometry, you can find out what is this vertical distance between node 0 and the electrode, and then take the ratio with respect to h, where h is r by 2. That is here explained, so I am not going into that. You are quite capable of doing this derivation. If you do that, you will find that S2 will come out to be 0.268h. That means this smaller vertical distance will come out to be 0.268 into h, where h is r by 2. Similarly, there could be, this subdivision could be such that h is r by 3. And in the same way, then two nodes, one here, you can see my mouse moving, and one here. Both will have two different S2, as it is indicated, S2 prime and S2 double prime. Again, you can apply your knowledge of trigonometry. Here, h is r by 3, as you can show at the bottom. You can see here, and apply your knowledge of trigonometry, which has been again explained, and you can find what is S2 prime and S2 double prime. And h, remember, will be r by 3. So such problems will be given for in the exams or assignments. You have to find it out. So this actually is the last note on the axisymmetric system, and then I'll have to move forward. And to what? Well, for that, I will have to now share one more file, for which actually in my last class there was a request. So let me show you that file. Yes. Now hopefully it will come on your screen now. Now is it coming on your screen? You can see gas insulated substation diagram.
Yes.
Yes, sir.
Yeah, good. So now just look carefully. I think last class, who asked me the question? Shreya, I think that you wanted an example of three-dimensional, three-dimensional, etc. Somebody asked me a question. Who was that?
Sir, it is me.
Just a minute. Can you identify yourself?
Yes, sir. Shubhoshri.
Shubhasri. Okay, you asked me that question. So I will try to explain that, and then I will go to the next part of the class notes. Okay, so now just look at this configuration. And I was trying to tell you also about the GIS as well as GIL. This is a GIS, and remember this GIS has everything. It will have the bus bars, it will have the CTPTs, it will have the circuit breaker, it will have event transformers. So GIS is a complete package which serves for to a huge area and a bulk power. But look at the compact design, which I tried to explain earlier also. And this is the actual diagram. And as you can see with this yellow line, this T junction here at the top is actually here it is the cross-sectional diagram shown. Now just take one by one, then it will be very interesting. See, look at the middle, there is a spherical object, and this spherical object, if you just take it itself, definitely it is axisymmetric. Then on the right as well as on the left, you can see this one. These are actually the insulators, whereas the yellow is actually the conductor. The slightly pink color are the insulators. So if you take the left side, this insulator conductor arrangement, or the right side insulator conductor arrangement, of course, it is axisymmetric because they are quite clearly rotationally symmetric. But now, when we have this assembly together, and remember this is a very compact design, then what we have to do, we have to compute the field for this assembly. Of course, we can do it for the individual component, but it is absolutely essential that we do it for the assembly. The moment we do it for the assembly, then it is no longer two-dimensional because we cannot say field is not varying in any one direction. It is no longer axisymmetric because it is no longer rotationally symmetric. So we have to go for the three-dimensional field computation. Here we will go straight away for a very conventional three-dimensional field computation. Now this is a little bit of relatively higher level of technology. I will show you a very simple example in our practical life. Now I will show you a separate diagram. I hope now you can see these are very normal transmission lines, high voltage transmission lines. And you know that if you see the left hand side diagram, this brown color is a very normal string insulator. If you take this very normal string insulator, it is definitely axisymmetric. Similarly, on the right side, you can see this is called a V string insulator. It is used when we have, special requirements. Now, on the left side, first we say this is called the dead end string insulator. That means the line is coming to an end, and then it will this connection will go to somewhere maybe in a transformer or so. So this is the end of the line. So this is called the dead end string insulators, and this is a very specific arrangement. Now, if you look at the two strings, this is, by the way, is a ceramic insulator. This is a, what is that called? Composite insulator, the white one, and that brown one is the ceramic insulator. Nowadays we have different materials, but when I have individual strings, they are axisymmetric. But whenever I look at this arrangement at the dead end of the line, then I have to compute the field for this assembly, not for just one particular string. And now when I do that, I cannot say it is two-dimensional. I cannot say it is rotationally symmetric. So I have to go for three-dimensional field calculation. Similarly, this V string, if you look at it, just string insulator is, of course, rotationally symmetric. But if I look at the V string, then it is no longer rotationally symmetric, no longer two-dimensional. So it becomes a three-dimensional field computation. Now, uh, in this right side diagram, there is one more practical information for you. Now, if you look carefully, can you see that in this V string insulator, and then on the middle also in this V string insulator, there are two conductors running, not one. Typically, you see one conductor. For example, left-hand side diagram, I have one conductor running. But here there are two conductors running. Can you tell me what is this?
Double circuit.
Double circuit. There is one suggestion, double circuit. Any other suggestion? Because this is the practical information, the practical life. Any
But
other suggestion? Yes?
bundled conductors.
Correct. Now you have given the correct answer. It is not a double circuit line, right? This is, you can see there are three phases here that you can look at the V. There are three V's which are supporting three phases, R, Y, B. But this is called bundle conductor system. Now, I always find that the students have a confusion about uh, what you have heard about ACSR conductor?
Yes.
ACSR.
Yes,
Yes, sir.
sir.
What is ACSR?
Middle core will be steel reinforced and outside will be aluminum.
Uh, so it is aluminum conductor, steel reinforced. Right. So, but they are also not one single conductor, right? They are called what is now stranded. I think you have heard the term stranded conductor because if I use just one cylinder, it is not mechanically very strong. So what we do, we take even the single conductor on the left hand side, whatever you are seeing, don't think it is one cylinder. No, never it is that. They are actually multiple cylinders of smaller dimension and they are twisted. They are then called as stranded conductor. So stranded conductor is a different thing and bundle conductor is a completely different thing. This is bundle conductor. Now, bundle conductor, you probably know that we use to increase the effective diameter of the conductor, and that is done to reduce the corona of the line because if the voltage level goes high, then to reduce corona, the diameter has to be increased. But diameter increase means it will be very heavyweight, etc., etc. So we go for this bundle conductor arrangement. Now there are a lot of arrangement. This is a two conductor bundle. You can have four conductor bundle. In India, two and four conductor bundle is very common, but you can also have 8 and 10 conductor bundle. The advantage is that each conductor is just like a normal conductor, so that you don't require any special conductor, right? Because you have to always understand that you have to order these conductors and buy it. So if you order anything special, cost increases. Secondly, for repairing, you always have to keep such conductors in your storeroom. That's a lot of money in your storeroom. But these are very normal conductors used everywhere. So if one conductor goes wrong, I will just bring any other conductor and replace it. That's a lot big advantage. So we increase this effective diameter by using this bundle conductor. Advantage is another is that each one carries say I ampere for the same voltage rating. So two conductor carries 2 I ampere. So your power capacity is straight away doubled. The power transmission capacity is straight away doubled. So these bundle conductor advantages are all there. If you want, you just read once more the bundle conductor. So this is another very typical case of three-dimensional field computation. I show you one more case. This is the gas insulated lines. On the left, this is a prototype. Central cylindrical conductor. Straight away, it will be two-dimensional. If the length is very long, if the length is short, it will be axisymmetric. Typically, remember, cylinder can be represented in both forms. If the cylinder is very long, we represent it as a two-dimension. If the cylinder length is small, we represent it as axisymmetric. But now, when I look at the entire arrangement, then I see that I have two post insulators here. Now, individually, these post insulators are shown on the right side. They are axisymmetric. But the moment I have the assembly, and on the right, you can see how the assembly is done. And this is the conductor, central conductor, the blue color. There is a hole here. And this cylindrical insulator, which is white color in the left diagram, that will go into the hole. So in this way, we will make a V-type configuration, and you can see on the left that truly V-type configuration. But once we do that, now I cannot say it is rotationally symmetric or two-dimensional. So I have to go for three-dimensional field calculation. So in this way, I can show many examples where maybe individual component is axisymmetric, but the whole thing is not axisymmetric. So I hope I could clear some confusion in your mind about these axisymmetric and three-dimensional and two-dimensional cases. But then comes the question that look at this arrangement itself, this GIL. This white one is actually a post insulator made of certain material, cast resin mainly. You can read if it's a small letter written, made of cast resin on the left side. So if you ask me, is it a single dielectric arrangement? My answer is, if you take the insulator only, yes, it is only single dielectric. But when I do the field computation, I have to remember that what is there surrounding the insulator. That is SF6 gas, which is another dielectric. And therefore, even if I compute the field only for the insulator without bothering about all other assemblies, still it is not a single dielectric arrangement, because there is another dielectric which is surrounding this insulator. So it's a two dielectric arrangement. Look at this diagram. Now just look at the string insulator on the left, the brown color. If I do it only this one, then it is only porcelain, so single dielectric. But I have to remember that this string insulator is always surrounded by atmospheric air, which is a dielectric. Therefore, this is also a two dielectric arrangement. So you can see that in our life, it is very difficult to get a single dielectric arrangement. Where we can say single dielectric? On the right side, if you just move away from the tower, then these conductors are running, and this conductor is surrounded by only air. So if you compute the field somewhere away from the tower, then it is a single dielectric arrangement, because only one dielectric is present, that is air. I show you one more figure here. This is a transformer bushing. Actually, the photograph is taken on top of the transformer. Here, somebody is standing on top of the transformer because this bushing got failed, so the photograph is taken during maintenance. Now, this bushing, you can really, why I am showing you this one, this is a very interesting photo which gives you the, what is there inside the bushing. Typically, this is called an oil field transformer bushing. Now, here you can see there will be a porcelain housing, which is just a part of the bushing, which covers the entire internal thing so that atmospheric air, atmospheric pollution, etc. doesn't affect. Then at the center, you have the paper insulation. Here you can see, which is cylindrical, and there will be a conductor running coaxially with this paper, and that conductor and that paper insulation arrangement will go into the tank. And in between the porcelain housing and that paper insulation, there is a gap, and we fill oil here. Now you can ask me that why there is a gap between this porcelain housing and the paper. I could have put porcelain straight away on the paper. The answer is yes, I can do that, but then there is slight, practical aspect we have to consider. You take two solid cylinders. The outer radius of one cylinder is equal to the inner radius of the other cylinder. So I repeat, two solid cylinders. Outer radius of one cylinder is equal to the inner radius of the other cylinder. So we can fit them together. But if they are two solid materials, can you ensure that their contact will be perfect at every point? We cannot do that. This is not possible if there are two solid materials. Even if in naked eye it looks okay, but the moment we magnify it, we'll see there is gap. And then what will be there in that gap? It will be air. And air is a very poor dielectric. So what will happen? There will be discharge in that gap. We can't allow that in high voltage system. So what we do is that we intentionally keep a gap between the porcelain housing and the paper, and then we'll fill it with air, oil, transformer oil. Then we ensure that there will be no air gap between the two. And oil is a much better dielectric, so we eliminate the possibility of discharge. So that's the technical part of it, that why there is a gap between the porcelain housing and the inside that paper. And then we have a slight pink color conical shape. What is this? This is very interesting. This is called the termination. If you just bring that paper, which is the cylindrical one, straight into that, you have to understand one thing, that this is going through the transformer tank, and transformer tank is zero potential. So at this point where this is going through the transformer tank is the most dangerous point for breakdown, because you have the high voltage conductor which may be at 400 kV, then you have the tank which is at zero. So you can see only this gap is withstanding that potential difference. So the design has to be very critical here. If you can see my mouse moving, and that's exactly where it has failed. So we have to put a special termination design. This is called the field stress control or field intensity control, so that the insulator is given a very special shape here, and thereby we control the field intensity, and thereby we control the breakdown. So this termination is used for bushing here, we use for cable. So wherever there is a conductor is being terminated at somewhere, we need this termination. So just keep it in mind that you just cannot bring a high voltage conductor and connect it to something. Then it will fail. So this is the other. So therefore, what I am trying to bring in this discussion, that here you can see there are multiple dielectric, isn't it? First you have the conductor inside, then you have paper, then you have transformer oil, then you have porcelain, then you have air. So how many insulators involved? Four. First paper, then oil, then porcelain, then air. So you can see just a very simple arrangement. I have four insulating materials involved. And now if I have to compute the field, I have to take all these materials and compute. Otherwise, I will not get the correct answer. So what is needed is, I have to go for multi-dielectric field computation. So I go for the multi-dielectric field computation. So I am, oops, where is it? Yeah. Ah. So two-dimensional multi-dielectric system. Actually, I can go for any 3D maxi symmetric. I'm not going into it. I'm just giving one example for your class that will be good for you. Now, what we do here, again, let me tell you that we have to do something very special here. First is, remember our basic assumption is that the field distribution is linear between two nodes, two connected nodes. Now, if two dielectric material is present between the two nodes, then this linearity is not possible because at the boundary there is a discontinuity. So what can be done? Well, this is done through the discretization itself. That means we discretize in such a way that one set of node is always on the boundary. Like here it is shown 2, 0 and 4 on the boundary. And other nodes are either on left side or right side of the boundary. So here node 1 is on the medium 1, node 3 is on the medium 2. This is a trick that we have to do, otherwise we cannot achieve accuracy. So that is done before the equation writing. That means this is done during the discretization itself. How? One set of nodes should be on the boundary. Once we do that, we have to also remember that since there are two dielectric medium, I cannot solve one Laplace's equation because the potential function has a discontinuity on the boundary, or in other words, we have two potential function. On the medium 1, I say the potential function is V. On the medium 2, I say the potential function is V prime. With the boundary condition that on the boundary, the potential must be same, because you cannot have two different potentials at one point, that is on the boundary. So, what we do, we have to find out a relationship between two potential functions. How do we do that? We use our knowledge of field theory boundary condition, that is the normal component of flux density remains constant. Now during the derivation, I will assume that 204 is on the y-axis. So x-axis direction is normal direction. So normal component of flux density is nothing but dx. So here you can see dx. So we write dx is equal to dx prime. Dx is on medium 1 side. Dx prime is on the medium 2 side, on the left side. Then dx is represented as epsilon 1 into Ex. Ex is electric field intensity. Then we find out this expression, or in other words, we say that we have a relationship between del v del x and del v prime del x. That means the two first order derivatives, they are related by the permittivity of the dielectric medium. After that, we write the nodal equation between 0 and 1. Here, between 0 and 1, my potential function is V, because 0 and 1 is medium 1. 0 and 3, potential function will be V prime, because this is medium 2. So equation 46, V3, potential function is V prime. V2 and V4, these two are on the boundary, so I can take either V or V prime. It doesn't matter, because on the boundary, the two potential functions are same. Therefore, here I have written 47 as V, that is V2, 48 also V4 as V. I have to solve two Laplace's equation, one for medium 1 using the potential function V. Since it is two-dimensional, I am taking del 2V del x square plus del 2V del y square is 0. Then medium 2, here the potential function is V prime. So del 2V prime del x square plus del 2V prime del y square is 0. And we recall that there is a relationship between del V prime and del V del x, where this k is a dimensionless quantity, which is the ratio of the two permittivities. So then we find out what is del 2V del x square from the Taylor series. By the way, there will be del V del x, because we cannot eliminate del V del x and del V prime del x from equation 45 and 46, because here we have del V del x, here we have del V prime del x. So what we do is we keep it there. del 2 b del x square and del 2 b prime del x square, and then we also write del 2 b del y square, and then we satisfy the two Laplace's equation 56 and 57. Now I have two equation and I have a term del v del x, so it will be straight away easy to eliminate that. So we eliminate it and do the algebra, we get equation 58. In terms of, again, all the electric potentials and the dimensionless quantity, which is K. So it's a linear equation and a scalar equation. And if you put epsilon equal to epsilon 2, it becomes a single dielectric system. So equation 58 reduces to your equation, which you have done already. Now, if I give you an example of this, how to apply it, here it is a two-dimensional system. So this circle, when translated along the z direction, which is perpendicular to the screen, it becomes a cylinder. And here the subdivision is such that the nodal distance h is r by 2. So this particular nodal distance, I have already earlier explained, it will become 0.268. There are two two dielectrics. On top you have air and bottom you have a porcelain. So this horizontal line here is the boundary. So we have subdivided in such a way that one set of nodes, that is 3 and 7, are on the boundary. 3 and 8 are on the boundary. 4 and 9 are on the porcelain side, and 1, 2, and 5, 6, 7, they are on the air side. And when I derive, I take medium 1 as air, medium 2 as 4, so K is 0.25. Now V1, I can use the equation for equal nodal distance for two-dimensional system. And this is a two-dimensional system, so the symmetry is half symmetry. That means right-hand side is equal to left-hand side. So node 1, I can assume that there is another node on the left-hand side which will be equal to V6. So that's what is written here. V1 is 2V6 plus V2 plus 100 by 4. Similarly, V2, I will assume there is another node on the left side, which is V7. So here V2, 2V7 plus V1 plus V3 by 4. Then V4, again equal nodal distance, and I will assume one node on the left hand side, which is equal to V9. So V4 is 2V9 plus V3 by 4. Then for equation 5, this is unequal nodal distance for two-dimensional system, not axisymmetric. So no question of symmetry around the axis. So you use that expression here. And of course, where is that? This is V5, right? So where is V5? Where is V5? Here, V5. This is the equation for unequal nodal distance. So now once we have done all that, and again then V6 and V7 will use equal nodal distance, V9 will use equal nodal distance. And the boundary nodes, I have assumed certain potential just for problem solving. Then comes the question of two nodes, which is V3 and V9. Now here I have to do some sort of a matching. Please remember that in our derivation, that diagram, this 1 was on the medium 1, 3 was on the medium 2, 2, 0, 4 were on the boundary. And K is epsilon 1 by epsilon 2. So I will assume that same way that for the node 3, I will assume that node 2 is on medium 1. This is then becomes V1. Then node 4 is on the medium 2. And therefore this will become V3 of the derivation. And then K is 1 by 4. And then 204 is along the boundary. So we'll assume one node on the left hand side, which is equal to V8. So V8 is equal to node 2, then we have V3 and then V4. And that's exactly you can see here V3. We have taken V2, V8, V4 and V8 and K is 0.25. That is epsilon 1 by epsilon 2. Similarly, if you take this node 8, then node number 7 is on the dielectric one side, so it becomes V1. Node number 9 is on the medium 2, so it becomes node number 3 of our derivation. V3 becomes node number 2 on our derivation, and then the potential 20 is the node number 4, because 204 is on the boundary. So you can see where is V9 here, sorry, V8 here you can see. V7, V3, V9, 20, and K is 1 by 4.25. And therefore, this is how we apply. So what I repeat, what you have to do always that you have to identify that for your target node, which one is your node 1, which is in medium 1, which one is your node 3, which is on the medium 4, medium 2, then node 204 will be along the boundary, because that is how we have developed the equation. Node number 1 is on medium 1, node number 3 is in medium 2, and 204 on boundary. So you have to match this nodal distribution, then only I can write the equation. So for any configuration that you can get, please match this nodal arrangement. So I think that will conclude this part, because I am not going into further detail. We can go much deeper, but I'll stop here. And on this one, if you have any questions, you have any questions? Okay, if you do not have any question, then I will stop sharing this one. Of course, notes I will send you, that you can rest assured. But there is one more thing I want to share. In our last class, I told you that there is something called that a field can be expressed as a one-dimensional field. Can anybody give me an idea? I told you, think about it. Have you thought about it? Can I express a field as one-dimensional? Two-dimensional I have explained.
So conductor in an open air.
No, that will become two-dimensional. It's a cylindrical conductor, so it will become two-dimensional. That means field will independent of the z direction. That is the length of the conductor. But when I am saying one-dimensional means just one particular dimension. Field is varying. Or in the other two direction, it is not varying. Okay, let me show you. This is a very, interesting way of presentation. Actually, you know it, but just thing is, we have to correlate this. Hopefully, you will see it now. Electric field due to a point charge. Can you see it now? Okay, good. Now, if you look at this diagram, then you will see that left-hand side is the representation of the spherical coordinate. So I just repeat once again what is spherical coordinate. Here, this is the origin. Then this point is P here, and the distance from origin to this point P is R, and that is one coordinate. Then, if you keep the origin fixed, and if you rotate this point, keeping R is equal to constant, what you are going to get? Can you tell me? No, I'm coming to that, but before that, I'm talking about the spherical coordinate system. If I keep the origin constant, And if I rotate R, what is the geometry you are getting?
Sir, a cone.
No, why? You are rotating R by 360 degree, keeping that origin constant. Why you will get a cone?
Circle.
Ah, yes,
Yes, sorry, sir.
it's a circle you are going to get. And then this angle 360 degree is measured not from this axis X or Y. This is actually measured from the Z axis. Theta, as you can see in the figure. This is the second coordinate. Then what is the third coordinate? That is interesting. Third coordinate is if you drop down a projection of that point P on the XY plane, that is the polar plane, then I can rotate it around the Z axis. Right? So, for example, here you can see this is R, right? So, R will have a component on the polar plane. Any idea what will be that component? Given theta is given. You drop down R on the polar plane. It will be R sine theta. R cos theta will be the component on the vertical axis, and if you drop down it on the, here, it will become the R sine theta. Then that R sine theta, if you rotate around the vertical axis, that is the third coordinate, that is phi. Here, the bottom is shown, here it is shown. So we have three coordinates, R, theta, and phi, which represents the spherical coordinate. Now, on the right, I have shown the field due to a point charge particle. Now, you all know that point charge particle at a radial distance, the potential is Q by 4 pi epsilon R. You all know that, right? And field intensity is Q by 4 pi epsilon R square. Now, look at that left-hand side diagram. That now this origin is the point, our point charge, and here is my point. I know the field, Q by 4 pi epsilon R, or it is, Q by 4 pi epsilon R square, fine. Now I am rotating rotating this point, keeping R constant, varying theta. Are you going to get different potential or field intensity?
No, sir.
You are not going to get, right? Then keeping R constant and theta constant, if I rotate this arrow around the z-axis, that means I am rotating around phi. I repeat, this arrow which is shown by this R, I keep this constant, R constant, I keep theta constant, and I rotate it around the vertical axis. That is, phi is varied from 0 to 360 degrees. What is the, are you going to get a different field?
No, sir.
You are not going. So now you can clearly see that field is not varying with the coordinate theta. Field is not varying with coordinate phi. It is only varying with R. So therefore, if you take the point charge or point charge particle, by the way, point charge particle is not fictitious. Let me tell you, it's not a fictitious thing. These are practical. Why? I can give you many examples. I'll give you just after this. So therefore, it is only varying with R. Therefore, if I represent in spherical coordinates, I can say this is one-dimensional field. But not in Cartesian. You cannot do it in Cartesian. If you do it in Cartesian, then with x, y, z it will vary. Now, as I said, that point charge particle is not. Also, before that, one more thing. In this spherical coordinate, when I varied varied theta with keeping R constant, we got a circle or a disk, I would say, right? It is not a circle, it is a disk. Because I told you that if a straight line is rotated or translated, I get a surface. So when this straight line R is rotated 360 degree, I get a disk. Tell me what happens when I rotate this R, keeping R length constant and theta constant around the vertical axis. What is the geometry you are getting? So you are straight away getting a cone. Now, this is something actually related to the coordinate system, which I actually don't know. This is something you must know about all this coordinate system. If time permits, I will tell you in my last class about some of the features of the coordinate system, because this is a knowledge which you should know, and this is universal. Anywhere you can apply this if you know the coordinate system and how one is converted to the others. And by the way, now the practical point, that point charge particle, is it a fictitious thing? The answer is no. See, I tell you, giving you an example. In our high voltage lab, we test a lot of equipment for commercial parties. So it is around 10 years back, one company came with a transformer for impulse testing. And they said that they have done some testing at their lab and it passed. But we tested and it failed. Then they asked a lot of questions, what can happen? We told this, that. So they went back and came back after 1 month, said, we have taken all sorts of protection. So we want to test. Okay, again we tested, again it failed. And they were totally confused that what happened. And we had a lot of discussions and finally they went back. Again came back after another month and this time it passed. Then I asked what actually you did finally. Then they said that they did many things, but finally what they did is that they cleaned this entire transformer winding by hot oil jet. Hot oil jet. Because, actually what happened that when they manufactured the transformer, when you machine a metal, not only you have the metal part, some waste material, but you also have metal dust, very fine metallic particles. And if you are not careful enough, these metal dusts will come and remain in your insulating system. These are very small particles, but they are metal, so they will be charged and they will create a hell of a lot of a problem from the field point of view. So when they cleaned with the hot oil jet, this metal dust finally got cleared, which was actually a problem during their manufacture. Now, these metal dusts are perfect example of point charge particles. And this happens in our life. It's not that these are fictitious. They happen. So remember that these point charge particles are very much possible. Similarly, it is also possible that cylindrical objects which are floating, but these are typically, some insulating material, the fibers. When an insulating material was cut, there was some insulating fibers, because most of our insulators are fibers. So, and these fibers are cylindrical in shape and they can remain in our insulating arrangement. And then we have what is called an impurity, which is cylindrical in shape in our system. So we can have impurities which are metal dusts. They are typically spherical in shape. We can have this sort of fibers in our system which are cylindrical in shape. So we have all these sort of impurities which are very much present in our shape. So we should never think that these are just something fictitious. No, they are not fictitious. They are very much in our system. So I hope I could explain that. So with this, I think now I have to conclude the FDM part, and in our next class, I will move on to the finite element. So then I conclude. Yeah. Anybody trying to say anything? Otherwise, you can log off.
Thank you, sir.
Thank you, sir.
Thank you, sir.